Okay, so we're live. Hi, everyone. Maybe I'll give it another minute or two because it seems like people are still filtering. Okay, I guess I'll get going. So, let me remind you, we're in the process of studying the Addario-Berry random graph, so last lecture we saw an upper bound on component sizes, or a stochastic comparison between the size of the component containing a fixed vertex in an Addario-Berry random graph and the size of a Poisson branching process. So that bound, let me remind you what that bound was. So we had that. So we're in the graph GNP. So if the parameter is satisfied that n minus 1p over 1 minus p is at most lambda, then the size of the component containing any fixed vertex is stochastically at most the size of a Poisson lambda BNMA tree. And let me just mention right away that so the range of parameters we'll be interested in is p of order 1 over n. Okay, and so for that range, this is the same as just np plus order 1 over n. And actually, so as an exercise for p, this is a very easy exercise. It's just rearrangement. But when p is at most 1 over n, this is actually at most np. This expression here. So you could just take lambda for p like that. You could just take lambda equals np to get this stochastic inequality. And I'll also use that for p at most sort of 1 plus little o 1 over n. This is well, let's say for p, well, let me leave it at that for the moment. What I actually want to do before I go on, so we're about to use this to prove some probability tail bounds on component sizes when p is a little bit bigger than 1 over n. But before I do that, I want to slightly strengthen the stochastic bound. This is developed in the exercises, but I want to highlight it to you so that you are aware of it, even if you're not doing the exercises. So for this same range of p, you can, so this stochastic domination can be strengthened in the following way. So to relate not just to the size of the whole tree, but the sizes of the generations. So to show that if I look at the neighborhoods, the sequence of neighborhoods nkv in the graph, that's stochastically at most the sequence of generation numbers. Remember the notation tk was the number of the set of nodes at height exactly k in the tree, or at distance exactly k from the root of the tree. And so this is true in that there exists a coupling so that the size of nkv is at most the size of tk for all k. Okay, and and that's nice because it allows one to start to get a bit of control not only on component sizes but also on distances within those components. So you know, you could use this to prove that you know, and this is also stated in the exercises in the notes. So you know, with P equals 1 minus epsilon over n, this implies that the probability that the largest distance from so what's this? This is the greatest distance of any vertex in the component of V away from V. The probability that that distance is bigger than K is at most 1 minus epsilon K. Okay, and then you can use similar ideas relating the behavior of a single vertex to the worst case behavior to show that this implies that if you maximize over any two vertices, so this is looking at the diameter of the graph, if you like. So the distance between V and W on the event that V and W are in the same component. So this is now looking at, so you take your random graph, you ask about over all pairs of vertices that live in the same component, what's the greatest distance? You can get a bound of the form log epsilon n divided by epsilon. Okay, so for epsilon constant, this is saying that in a subcritical error-de-Shrenier random graph, the greatest pairwise distance is logarithmic, but this works even when epsilon is depending on n. Okay, so that's all of this is in the way of exercise. This is the fact I want to now use to prove upper bounds on component sizes. So let me bring it down to the next page and continue on from there. So the proposition I'd like to prove to you now is, I think I stated this at the end of last lecture as well. So we fix a sequence epsilon n positive and we set P of n to be 1 plus epsilon n over n. And then we said that, so in GNP, for any positive integer s, the probability that the largest component has size at least s is at most 2 plus little o1 epsilon n over s plus order 1 times n over s to the 3/2. Okay, so now I'd like to turn to the proof of that. So we'll write, let me define, so lambda to be 1 plus epsilon plus 2 over n, okay? And then you can check, that's just to give myself a little bit of wiggle room, that lambda is bigger than n minus 1p over 1 minus p for n large. Okay, so so this stochastic inequality here tells me that the probability that a single component size is bigger than s is at most the probability that Poisson lambda Bieniemy has size bigger than s, and I'll just bound that by the probability that that tree is infinite plus the probability that its size is bigger than s, given that it's finite. Okay, so that's I'm not doing anything there. I'm just using that one of these two things has to happen if the tree is s size bigger than s. Either it's infinite or it's finite and bigger than s. Okay, and the first term we know is just theta of lambda, which is at most remember we talked a little bit about the shape of this Poisson survival probability function. It sort of has, it's concave after 1, and it has slope 2 from the right, where it first takes off. So that means it always stays below the 2 times lambda minus 1. Okay, so this is at most 2 lambda minus 1, which is 2 plus little o1 times epsilon. Okay, so that's an upper bound on the first term. And then for the second term, right, we said that, so given that t is finite, it's distributed as some t hat, which is a Poisson lambda hat biennetry. So this was the duality result for branching processes. Okay, and here remember the dual this is the Poisson dual parameter. It's lambda times 1 minus theta of lambda. Okay, and in particular, it's at most 1. Okay, so let's just use that bound to say that. So this we have, the probability that t is at least s, given that t is finite, is at most the probability that Poisson 1 BNMA has size at least s. Okay, so when lambda is bigger than 1, lambda hat is strictly less than 1, but I'll just use that it's at most 1 for an upper bound. We saw that this was order 1 over s to the half. Okay, and so let's just combine. We have an upper bound order 1 over s to the half for this term, 2 plus little o1 epsilon for that term. So we get the bound probability CV is at least s is at most. So the sum of those two things. Okay, and now we use the lemma from last time, which said that the probability that the maximum component size is at least k is at most n over k times the probability that, well, C1, I wrote it for before, so so this bound was for any vertex v. So let's take v to be vertex 1 has size at least k, and that gives us the bound. So now the probability that C max is bigger than S is at most. So we get 2 plus little o1, and then epsilon n over S. That's the first term times n over S, and then the second term times n over S is order 1 times n over S to the 3/2. Okay, so that's the bound that we claimed, right? So we have this epsilon n over S is the key point here, and n over S to the 3/2 is the key point here. Okay. Fine. So what does that tell us? Well, I don't have to scroll back up to this theorem statement because I've rewritten the conclusion right at the bottom. How much can we get out of this? We're not going to get anything if S is less than n to the 2/3, because then we're just bounding this probability from above by something bigger than 1, right? So that's a first remark. So this is useless for S less than n to the 2/3, but it does tell us, as soon as S is bigger, it tells us something. So it tells us that, let's look at the range where epsilon is order n to the minus a third, okay, then this gives that for any x at least 1, say, the probability that the largest component has size bigger than x n to the 2/3 is order 1 over x. Okay, and that's just because in this case, if we take s to be x n to the 2/3, then epsilon n over s is order n to the 2/3 over s because of our assumption on epsilon here. So that's order 1 over x. And then the other term, n over s to the 3/2, is actually order 1 over x to the 3/2. So it's an even better bound. Okay. So that's easy. And this, this scaling, I sort of pulled it out of thin air, except that we already saw that this scaling emerge as as some sort of barrier when we were looking at subcritical at probabilities less than 1 over n. We got into trouble when epsilon was around this value, and moreover, once you notice that we can't do anything with this term until s is at least n to the 2/3, then actually the scaling epsilon of order n to the minus third is kind of forced on you to get something non-trivial out of this term. If you want to, as soon as this term starts to be small, then this ratio here is of order n to the 3rd, and then if we want this term to be small, n to the minus a 3rd is where you start to get bounds. Okay, so somehow that scaling is again just showing up naturally as a facet of the problem. Okay, but we can also think about what we get if epsilon is potentially bigger than this. So it's worth stating that as well. So as a second corollary, so if we know that, so let's say that epsilon, is at least order n to the 3rd. So limit epsilon n times n to the 3rd is positive. Okay, then in this case, for x at least 1, we can look at the probability that the largest component has size bigger than x times epsilon n. Okay, and what will we get out of our two terms? So if we take s to be epsilon n times x, then here we're getting order 1 over x. Okay, so that's the first term is giving us order 1 over x. And the second term is giving us, so order 1 times n divided by x epsilon n to the 3/2. Okay, and we can rewrite that. So that's order 1 over x. And then the second term is order 1 times 1 over x to the 3/2, and then 1 over epsilon cubed n to the 1/2, right? We have a epsilon to the 3/2 here, and we're only left with a power n to the 1/2. Okay, and so in this range, epsilon cubed n is bounded away from 0, so this term is just acting like at most like a constant, and so so this whole second term is order 1 over x to the 3/2, and the bound we get is order 1 over x. Okay, so so when epsilon is this small, we get bounds on the probability x is much bigger than n to the 2/3, and when epsilon is bigger than that, we get bounds on the probability the largest component has size bigger than about epsilon n. Okay, and so if we combine those, into a single statement, we can write that for all x at least 1, the probability that the largest component has size bigger than x times the maximum of epsilon n and n to the 2/3 is order 1 over x. Okay, and so this isn't, and I guess this is for all, if you like, for all, say, p at least 1 over n. Okay, but if it's true for p at least 1 over n, then actually it's also true. We were using p, we were looking at p in this range, but you know, if this bound is true for, oh no, that was a little bit hasty. Let's think about what range of p we had here. So this was for, this was all for yeah, p is 1 plus epsilon over n, and so I should write here for all p at least 1 over n with epsilon equals np minus 1. That's the correct scaling in this thing. Okay, so again, this isn't it isn't sort of obvious at this point, but this is actually a tight bound. So this really, this dichotomy between the two potential scalings really exists, and those are the correct bounds in both cases. Okay, so there's one point in this proof where you might think that one can extract a little bit more, and because, you know, all we did was we said we used comparison with the branching process, and then we used branching process duality to say that this supercritical tree conditioned on being finite looks like a subcritical tree, and but then I just said, well, if it's subcritical, it's at most critical. And you might try to say, well, if it's subcritical, you know, actually we can get better tail bounds than what I stated here. Why don't you try to exploit that? Okay, and you can try to exploit that. You know, so a natural attempt to so let me say one way to try to strengthen these bounds would be to use that t hat is Poisson lambda hat geometry. Okay, and then what you end up with from that is bounds of the form. So the point is that so if lambda is 1 plus epsilon, then lambda hat is 1 minus epsilon, 1 plus a low 1. Okay, and we discussed last time sort of bounds on the size for subcritical geometries. So this, you know, in this case, we get bounds of the form so the probability that t hat has size m is so order 1 over m to the 3/2, and then we get an e to the minus m epsilon squared on 2 times 1 plus the low 1. Okay, so this is a bound that we already stated last time, and if you try to carry this through, use this. So before, you know, in the previous argument, we just had this order 1 over m to the 3/2 that we were using. Now we're getting this what looks like it might be an improvement, and if you try carrying so this improved bound through the argument, you get you end up with a bound of the form probability that the largest component has size bigger than s is at most, so this epsilon n over s term we had before, and then n over s to the 3/2 e to the minus epsilon squared s on 2. Okay, and So if you that's sorry, epsilon squared s on 2. Okay, but this if you take s to be epsilon n in this, you see that you need or say x epsilon n, then this gives a bound. So when is this good? Well, the first term we get 2 plus little o 1 over x. Then for the second term, we get so 1 over so x cubed epsilon cubed n to the half e to the minus x over 2 and then epsilon cubed n. Right, so we had an epsilon squared and we pick up another factor epsilon, and so you see again you need epsilon x to be bigger than n to the minus a third to get a non-trivial bound out of this. So you don't do any better than an n to the 2/3 term here. Okay, so you need this to be at least n to the minus a third to get a non-trivial bound. Okay, so this bit was a little bit hasty, but I sort of let myself be sketchy because the message is really just well, it's a repetition of the same argument, and it doesn't yield anything better. You sort of try to do better, and you realize that your attempt is useless. Okay, so let's so again this scaling n to the minus a third has popped up. Okay, and the size n to the 2/3 has popped up. The next theorem that I'll prove, and that'll take a bit of work, so starting today and continuing on Monday, will indeed so make this upper bound a little, well, we'll see how this upper bound is tight, and we'll see how this n to the minus a third really does arise as a special scaling. But before I state that, I want to tell you a theorem which I won't prove right now, and I will give you some indication in the course of how to prove, but won't give a full proof. So this dates back to the mid-90s, and it indeed sort of identifies this critical scaling. So this is from 94, and then there's related work by David Aldous from 1997. So this says that if we fix real constant c and let p be 1 over n, so let me write it as 1 plus c over n to the third, so that's our epsilon divided by n. Okay, then this largest component that we've been studying indeed has size n to the 2/3 in probability, and its distribution is so on that scale n to the 2/3, its size converges in distribution to some random variable z, which has finite expectation. So for some random variable. And I guess maybe I want to say it's non-trivial as well. So positive finite expectation. Okay. Okay, so that's that sort of, even though I'm not proving that right now, says that this scaling we've been putting our finger on is not an artifact. It's a genuine facet of the problem. Okay. Let me before I state what I'm going to do next is state and start to prove a law of large numbers for the size of the largest component once we're past this value of p. So that's, you have to get larger than this to start to see sort of concentration of the size of the largest component. This theorem tells you that for this sort of scaling of probabilities, the largest component has sort of a random size to first order. But once p gets just a bit bigger than this, we already see a deterministic size. Okay, but just before we get there, I want to turn back to the subcritical case for just a moment, because we haven't really fully discussed what happens there. We've or let's say we haven't exhausted the tools we've developed in the subcritical case. So this is for p of the form 1 minus epsilon over n. Okay, so epsilon positive. Then we have a coupling. So the coupling with Bien-Aimé gives us the bound. So the probability that the component has size at least x on epsilon squared is at most the probability that a Poisson 1 minus epsilon Bien-Aimé has size at least x on epsilon squared. And we saw yesterday that that's order epsilon over x to the half e to the minus x on 2. Okay, so whereas so the bounds we got just from doing first moment calculations, remember, told us that in the subcritical regime, so when p is less than 1 over n, the largest component had size at most root n. Using this coupling, we do quite a bit better because we have this exponential gain. Okay, and so one of the exercises in the notes, not too hard, is to use this to prove that that in this, so for this subcritical case, the largest component has size order log n epsilon cubed over epsilon squared in probability. Okay, so you can there's just one or two steps to get from here to there, and I sort of spell those out in the exercises, so it shouldn't be too hard to do. So no, this for this you don't need epsilon. Someone asked in the chat, do you need epsilon fixed now? And it's true when epsilon is fixed. This is just saying Cmax is logarithmic, but in fact this this argument works for epsilon varying as well. Yeah. Okay. So if there are no questions about that, then now I'd like to state the theorem that will occupy the rest of this lecture and probably the following one as well. Okay, so we're turning to so first order behavior of Cmax when p is bigger than 1 over n. Okay, and really I actually want p bigger than 1 over n plus this n to the minus a third correction, as you'll see. Okay, so here's our target, and so it kind of handles it does many things at once, even though it's in like a single unified statement. So we'll fix so p of the which I'll write in two ways. So lambda over n, which I'll also write as 1 plus epsilon over n. Okay, and I'm going to suppose that so this epsilon over n to the third tends to infinity. So precisely just above the regime handled by the theorem I stated just before. And I'll also assume that the numerator here is bounded. Okay, so that there's some absolute constant m such that the numerator stays at most m. Okay, then the size of the largest component, so that I should say maybe in GNPN, the size of the largest component divided by n times theta lambda converges in probability to 1. Okay, so we again precisely see this Poisson survival probability cropping up. It's intimately connected to the problem. Okay, and so in the case where p is just barely bigger than 1 over n, so this epsilon tends to 0, which isn't required for the problem, but in that case, it says that if epsilon tends to 0, and so n to the minus a third epsilon tends to infinity, then the size of C max. So in this case, we know that this theta of 1 plus epsilon is 2 epsilon times 1 plus little o1, right? And so then we can rewrite this statement as saying that the size of the largest component divided by 2n epsilon n converges in probability to 1. Okay. So before we get into the proof, let me make a couple of remarks. Is there any questions about the statement of the theorem? So it really is just a weak law of large numbers, if you like. It describes the asymptotic first order behavior of the largest component. Okay, so let's say that, so first historically, this is so this law of large numbers for this range of p goes back to work of Bela-Bolobash in 1984. Okay, he didn't actually, I think he didn't quite get down to this assumption. He needed epsilon, he needed this ratio to go to infinity at some logarithmic rate, if I remember correctly. So he sort of almost did this, but maybe not the full range. But effectively, I think this is dealing with epsilon tending to 0 in the first place was certainly his result. So let me say that you can go past the first order behavior to the second order behavior as well. And the method I'm going to use to prove this theorem can actually be built upon to study fluctuations as well as first order behavior. Okay, so that's part of why there are a number of different proofs you can use for this. The one I'm using is fairly well suited to studying fluctuations as well. So let me tell you without proof what's known about fluctuations. It's not that hard to state. What do you do when you want a central limit theorem? You need to subtract off the mean and then divide by an appropriate scaling. So if we subtract off the mean, then the appropriate scaling is of order n to the half, as you guess. So it's something n to the half. And the something is quite explicit. So it's theta lambda 1 minus theta lambda all divided by 1 minus lambda hat squared. So okay, so this here lambda hat again is lambda 1 minus theta lambda. It's the Poisson dual parameter. Okay, and this, so this whole thing converges in distribution now to a standard Gaussian. Okay, and that's a result of Boris Pittel and Nick Wormold from 2005. Okay, so yeah, I won't prove this, but the methods that we'll use to prove this theorem get you most of the way, but the rest is still another lecture or two, and I don't want to spend the time. So there's one more remark I'd like to make. So it might seem a little bit unfortunate that that I stop at some fixed value m here. Okay, but this also implies that if p of n is like lambda n over n, and lambda n tends to infinity, right? Then well, for any sequence, we could always take lambda to be a constant sequence, lambda equal to a fixed value n. And then this would just tell us that for p constant lambda over n, we'd have a law of large numbers, right? Which says that the largest component occupies a proportion theta lambda of all of the vertices. Okay, but theta of lambda tends to 1 as lambda tends to infinity, right? The survival probability of a Poisson branching process tends to 1 as the mean gets large. Okay, so and the size of the largest component also certainly gets larger as the edge probability gets larger. Okay, and so together those facts imply that in this case, the size of the largest component divided by n converges in probability to 1. Okay, so in fact, just sort of this straightforward coupling that says when you increase p, the largest component gets larger, together with this result, tells you what happens for larger p. So the restriction, this upper bound restriction, really isn't much of a restriction. Okay, it'll just be useful in the proof. Okay, any questions about the statement before we sort of start to develop our tools? So so the tool should feel somewhat familiar because it's related to the depth first Q process that we use for studying BNA matrices. Okay, but in the setting of graphs, it's a little bit more involved to set up. So this is the key tool for the proof. So it's exploration process for GNP, and well, in fact, so it makes sense to define this for any graph, but we'll only use it for the Addario-Berry random graph. So I'll just give you the definition in that specific setting. Okay, so so I'll call it the depth first Q process, like for BNA matrices. Okay, so it'll have steps from n plus 1 steps from 0 to n, and at any given time, we have 3 sorts of vertices. So the vertices are partitioned into explored, active, and unexplored vertices. Okay, and the initialization is just that at time 0, we haven't explored anything, nothing is active, and everything is unexplored. Okay. And we'll maintain throughout that well, yeah. So I said this this triple is always a partition of the vertex set. Okay. So so the priority of a vertex is the time at which it leaves the unexplored set. Okay, so that means that vertices activated later vertices that are discovered later have higher priority. And that's what makes this depth first rather than say breadth first. Okay, okay, so here's how here's what a step of the exploration looks like. So this is going from from time t minus 1 to time t. Okay, so so we want to explore a vertex, and exploring a vertex is always going to mean revealing the neighbors of that vertex among the previously unexplored part of the graph. Okay, so the question is, how do we choose what vertex to explore? So if any active vertices, we'll choose one of them. So if this is non-empty, then we'll let VT be the element of AT minus 1 with highest priority. And so the tie-breaking rule is, as usual, smallest label. Okay. So that's if there's something that we've already discovered to explore. If there isn't, then we'll just let VT be the smallest element of the unexplored set. So of UT minus 1. Okay. And now, so having decided which vertex we're going to explore, we explore it. So that means we'll add all its neighbors to the active set. So AT is AT minus 1. We remove VT, but then we add in any previously unexplored neighbors of VT to the active set. Okay, we've now explored VT, so we put it into the explored set. So ET is ET minus 1 union VT, and the unexplored set, we have to remove VT. So just a terminological note. So I'll allow myself to write this vertex might not be an element of this set, but if it isn't, then this just when I try to remove something from a set it wasn't in the first place, then I just haven't changed the set. Okay, so this makes sense even if VT isn't in UT minus 1. And then I also need to remove all the stuff that I just discovered. So VT and a VT union UT minus 1. Okay, so that's the whole. That's one step of the exploration. I pick a vertex according to the priority rule. If there's no vertices already active, then I just choose a vertex, the smallest unexplored vertex to explore. I reveal its previously unexplored neighbors. They become active, and that vertex becomes explored. Okay, so this process always has the property that so we maintain because the these three sets from a partition, then their size always adds to n. Okay, but also we add exactly one element to ET at each step, right? There's one vertex explored at each step. So this parameter is always T. Okay, so that also says that the number of active vertices plus the number of unexplored vertices is always equal to n minus T, if you like. Okay, so let's go through a quick example. I think many of you have seen this before, and it'll feel, probably feels a bit slow, but I want to point out a feature of the exploration process, which is how the sort of presence or absence of certain edges affects the exploration. So I think it's worth going through the example. But I'll start. I'm going to do an exploration of this graph. So a graph with so imagine that this is my random graph. It has 4 connected components, and let's just think about how the sets change. Okay, so I don't need to tell you all of the sets because if you know any 2 of them, you can work out the third one. And if you know, and actually, if you know how 2 of them change, you can work out the third one as well. So I'm just going to record what vertex is explored and what vertices are active as we go along. Okay, so the first vertex, so at time 0, nothing has been explored, nothing is active, and so we just start by choosing the smallest labeled vertex from everything in order to explore. So that means V1 will be 1, and when we explore its neighbors, we get the vertices 8 and 13. Okay. Now these 2 have equal priority. 8 has smaller labels, so the second vertex to be explored will be 8, and the second active set now contains the new neighbors of 8, which are 2 and 7, plus 13. Okay, and I just want to record, I'm going to draw this edge here. Maybe I'll draw it in some light gray color. It didn't matter whether or not this edge was here in the process, right? I'm only exploring, the process is determined by the edges to new parts of the graph, to the previously unexplored part. So whether or not this edge is present doesn't matter. Okay. So in the next step, we explore so top priority vertex. 2 was discovered more recently than 13, and it has a smaller label than 7. So V3 will be 2. 2 doesn't have any new neighbors, so that means that A3 is just 7, 13. Okay. It didn't matter whether this edge was present or not for that step, and it also didn't matter whether this edge was present or not, right? Those any edge from V3 to the rest of A2 doesn't change the process. Those are already activated vertices. Okay. So V4 will be 7. That's the most recently discovered vertex. But it doesn't have any new neighbors. So when we explore it, nothing gets added to the active set. So A4 is 13. Okay, and then finally, when we explore vertex 13, we don't discover anything new, so the active set becomes the empty set. And that tells us that there's nothing left to explore. We've completed the exploration of this connected component. So at the next step, I won't go through all 4 steps sort of in painstaking detail unless there's confusion, but the next, I'll write down at least one more step. So what do we do when the active set is empty? We take the smallest label from the rest of the graph. So in that case, that's the label 3, and that's where we start our search. Okay, so V6 will be 3, and then A6 is we explore the neighbors of 3. So that's just the set 11, and then we'll go from there. Okay, so the choice, so I'm just looking at the chat. The priorities of points are from the original definition. So if you like, so I'm saying things that are added, if you think of this as this list, you see I'm always putting the new terms on the front of the list, and I'm putting them on the front of the list in increasing order of label. And so then if you always pull the first term off the list, you'll be precisely agreeing with my priority rule. That's the depth first search. It's the stack in computer science terminology. It's the stack perspective. You're taking last in first out rather than first in first out. If you put the new stuff you discover on the back of the queue, then you'd be doing breadth first search rather than depth first search. Someone says, why are there 2 7s? So the yellow 7, oh, sorry, yes. So let's call that, I don't know, is there a label missing here from 1 to 15 17. I can use? Let's call it L. Okay, since I'm not going to go through the rest of the, I guess, there has to be something missing by pigeonhole. What is it? 4, I guess. Okay, so that's 4. Thanks. Yeah. So right. So is any more questions about the definition of the procedure? So the point I was making with these gray edges, let me write that down. So the presence or absence of edges from VI to vertices in AI minus 1 does not change the process. Okay, and someone has pointed out that 9 should also be a 5, say. Okay. So, in the second component, for example, that means that the edges from 6 to 9 or 10 could be present or absent, and the edge from 15 to 10 could be present or absent. And in the last component, this edge from 12 to 14 could be present or absent, and nothing changes in the process. Okay. That's the process. That's the exploration process we'll study to prove this law of large numbers. Let me give myself, a version of. So what did we do for trees? Once we had this exploration process, we tracked this sum of degrees minus 1, which was telling us, if you in this language, that's saying we explore one vertex, it is removed from the active set. That gives us a sort of -1 to the size. And then we get some new number of neighbors, and that corresponds to the number of children in the tree process. Okay, so so I want to do the same thing here to track that sort of how the active vertices evolve over time with the function. So let me give myself a couple of definitions. One is so kappa of t for the number of components discovered by step t. And so then kappa of n is the number of components of the whole graph. Okay, and I'll let the times at which those components become fully explored be called Tj, so for j from 1 up to kappa. So these are the times when the exploration of a component concludes. Okay, so these are, in other words, these are the times I such that AI is empty. Okay. Now, so the function that will describe the exploration. So the variables will be these the number of newly discovered vertices at each step. So that was so the that's the number of neighbors of VI and UI minus 1, and we take away 1 because we explore VI, and then we set SI to be the sum for I from 1 to t of xi. Okay, so so in the let's plot that for the example that we just had here. And let me also actually bring the graphs over, though I have to make some changes, right? That was supposed to be a 4. And that's a 5, though it doesn't really matter for this step. Right. So we begin by uncovering
5 row.
Sorry? So right. So in the first step, we discover 2 vertices. So our walk increases by 1. In the next step, we discover another 2 vertices. Our walk increases by 1 again. Then the next 3 steps, we discover no new vertices. Our walk decreases by 1, decreases by 1, decreases by 1. And that corresponds to the time when the exploration of the first component is finished. Okay. Then we explore, so now we're going to start at the next step from vertex 3. When we explore the neighbors of vertex 3, we find 1 new vertex, so the walk increases by 1 minus 1, it stays unchanged. Okay, then we discover 3 new vertices, the walk increases by 2. Right. 6 has no new neighbors, so the walk decreases by 1. 9 has 1 new neighbor, 15, so the walk stays stationary. And then 15 and 10 each have no new neighbors, so the walk decreases by 1 twice in a row. Okay, now we've completed the exploration of the second component. When we go on to explore the third component, it has no new neighbors, so we immediately take a negative step. And then when we explore the fourth component, we'll make a positive step because 5 has 2 neighbors, followed by 2 negative steps. Okay, so this is the process S that I've just plotted. Okay, and you can sort of instantly see from the drawing that it gives us another representation of these times Tj. The time when we finish exploring the jth component is the same as the first time t, that this sum of xi for I from 1 to t is equal to minus j, right? And so here we hit minus 1, we've finished our exploration of the first component. Hit minus 2 when we finish exploring the second component. Hit minus 3 when we finished exploring the third component. And minus 4 when we finish exploring the fourth component. Okay. So as Lior has pointed out in the chat, this is literally the next thing. He's not a plant. It's just quick at noticing the key points. This in particular, you can deduce from this that the number of active vertices at any given time is st plus kappa t. Okay. So, maybe I'll just quickly verify this. It takes 150 seconds or something. So I think it's worth just making it clear by sort of quickly checking. There's just two cases to check. It's true at time 0. And then for larger times, there's two possibilities. So one is if we're in the midst of exploring a component, we're not at the end, right? Then AT is AT minus 1. We remove VT, and then we add these neighbors. Okay, and so so we get that the size of AT is the size of AT minus 1 plus the size of the newly discovered set. Okay, and that's just AT minus 1 plus, well, rather this difference here is XT. Okay, and that's the same as AT minus 1 plus XT plus kappa t minus 1, because in this case we're not finishing the exploration of a component, so this difference is 0. Okay, so that's one possibility, and then the other possibility is that we are concluding the exploration of a component, and in that case we have so what happens when we finish exploring a component, then the newly active set just consists, we take some new vertex VT, which comes out of the unexplored set, right? We explore its neighborhood and we put all of those into the active set. So that's n of VT intersect UT minus 1. Okay, and that's equal to XT plus 1 this time, okay, which we can also write as AT minus 1 plus XT plus 1, because AT minus 1 was empty. I haven't changed anything there. Okay. And now at times like this, these are the times when kappa changes. So I can write that as AT minus 1 plus XT plus kappa t minus 1. Okay. And and because S is just the sum of the X's, this precisely gives this identity by induction. Okay, so okay, so we can see from this process how many components we've explored so far and how many active vertices there are. Okay, and if we don't care about these gray edges and we don't care about the precise labels, then that's all we need to know. Okay, so this graph here gives us full information about the component sizes, but not about their internal structure. Well, not everything about their internal structure. It actually does reveal for us a particular spanning tree of the graphs, but not whether some additional edges are present or absent. Okay. Right. Okay. So the question is, how does this? We're interested in understanding this process when the graph is a random graph. Okay. So let's think about the distribution of its steps. In the case of DNA matrices, it was easy, right? These increments were just IID with some law. But in the current case, they're not IID anymore. Okay, because as the graph goes on, there's less and less of the graph left to explore. So the distribution of how many new vertices you discover changes. Okay, so let's write Fi for the filtration generated by the process. Up to step I. Okay, and let me also write so I need one more definition. So I'll write ui prime for ui minus vi plus 1. Okay, so this, again, this is the same as ui if ai is not 0, if ai is not empty, but it's different otherwise. Okay. Then if I condition on the information up to time I minus 1, then the new increment, so the number of newly discovered vertices is binomially distributed with mean, it's binomial with parameters size of ui prime and p. Okay, because so if the active set wasn't empty, then I just explore a binomial subset of ui minus 1 at the next step. Each edge to the unexplored set is independently present with probability p. But if this set was empty, then first I remove the next vertex from the unexplored set, and then I explore the neighbors in the rest of the graph. Okay, so I have to, the number of potential neighbors goes down by 1 in that case. Okay, so this is to say that the probability that that this set has size k given fi minus 1 is the size of ui minus 1 prime, choose k, p to the k, 1 minus p to the ui minus 1 prime minus k. Okay. Does that, should I say more about that, or is that, does this make sense to everyone? Right, so you've got the part you've explored, you've got the part that you haven't explored, and then you're just saying each edge from here to here is independently present with probability p, except that if we had just finished exploring a component, then first we peel off one vertex from here to explore. Okay, so that's sort of telling us about the distribution of these steps x, right? Because x was just this size minus 1. Okay, and now we're saying that that's basically just a binomial subset of the remainder of the graph. Okay, and so heuristically, at least, that suggests how the process is going to evolve. When there's at least one active vertex, that tells us that the expected size of ui plus 1 given fi is like ui times 1 minus p. Okay, and so we should have that ut is roughly n times 1 minus p to the t, which is like n e to the minus pt. Okay. Well, I mean, you might object that so at this step, this heuristic only applies when at times when there's an active vertex. Okay, and sometimes there's no active vertex, but you know, let's remember. So we're trying to do an analysis of a graph where so p is bigger than 1 over n. So the average number of neighbors that's found in a given step is bigger than 1. Okay. So heuristically, you can imagine that at least at the start of the process, you typically discover more, you know, the size of this active set, you expect at least at the beginning to be increasing. And so then sort of on average, you don't expect to be discovering lots of new components at the start. So at least for a while, at the beginning of the process, when I is not too large, you can sort of hope that that the heuristic of what happens when the active set is non-empty is a predictor of the whole process. Okay, so that's this is not you know, particularly rigorous, but at least seeing these binomials, you know, saying that the exploration is always a binomial subset of what remains, does somehow suggest some scaling roughly like this. And so now, if we use that, if you sort of are willing to sort of stick with me on this for a second, then you know, we can also try to use this to think about what it says about how the active set is evolving. You know, so using that, we said that the size of the active set is n minus t minus the size of the unexplored set. Okay, this gives that, you know, AT would then roughly be like n minus t minus n times 1 minus p to the t, okay, which is like n minus t minus n e to the minus pt. Okay. So let's you know, then the most of the proof. So it's, I think I see a comment from one person in the chat saying I'm a little confused. I think that's reasonable because I'm not being, well, I mean, if you have questions about this part of the story, I'm happy to clarify them. This part, you know, the bulk of the proof of the law of large numbers is in making this heuristic rigorous and quantitative. So there is something to understand here, but you know, I'd like you to sort of well, try to think a little bit about this before we make it rigorous, because it's useful to have some sense to be able to sort of follow along with this story, even if we haven't filled in all the mathematical details. Okay, maybe one way I can make this heuristic a little bit more compelling is to say the following. In this process, you know, each time the active set was empty, we added one new vertex to the to start exploring from. Okay. But if instead of adding exactly one new vertex, I decided to just add a binomial random set of vertices to start from. Okay, so I just say, rather than picking one new active vertex, let's make each vertex over here that isn't already active, that's unexplored, independently active with probability p. Okay, so I might get none, I might get lots, but I'm just going to pick a binomial subset to make active at each step. If I do that, then literally at every step of the process, the proportion of unexplored vertices goes down by a factor p on average. So if I chose a random subset rather than exactly one to explore from, then this heuristic here wouldn't be a heuristic. It would be exactly an exact identity in expectation. On average, every step I would go down by proportion 1 minus p. Okay, and so I mean, we're not doing that. We're picking one new vertex at a time. But as long as sort of the you know, as long as we don't explore too many components, as long as this kappa doesn't get too big, then the difference between those two processes shouldn't get very large. Okay, so that's that's one way to sort of maybe get a little bit more intuition for the heuristic, is by imagining that instead of picking one new vertex each time the active set is empty, you pick a random number of vertices. Okay, so so let's think about this function here for a second. Okay, when p is bigger than 1 over n, you know, at the start, this n minus t term, well, it has slope 1. It changes by 1 when you change t by 1. And this term has slope bigger than 1. Okay, so for t small at least, this heuristic suggests that the size of the active set will increase over time. And then eventually, once you go on for a while, you know, as t gets larger, this term gets closer to 0. The slope, the relation between the two changes, and this heuristic starts to suggest that the size of the active set should get smaller. Okay, so that's maybe a little bit too vague now, but let me give you a picture, and maybe that will help. So so here's this is a heuristic plot of what? So so on the top I have the line. So I'm going to divide this whole expression here through by n. Okay, so on the top I have the line 1 minus t over n. Okay, and on the bottom I have the curve 1 minus p to the t. Okay, so that's 1 minus p to the t. So they meet, these two curves agree at t equals 0. Okay, this is a convex function, right? It approaches 0 as t tends to infinity, whereas this linear function will just hit and cross 0 at some point. Okay, and here so somewhere over here I've plotted the point at which they meet. So let's let t and p be the largest real solution to the equation n minus t minus n 1 minus p to the t equals 0. Okay, so that's this point here, t and p, where these two curves meet. Okay, then so t and p is in fact you know, n times theta of np basically. Okay, so let me so actually theta of np we called lambda. Okay, so this was this point where these two curves cross is basically at the thing that's the denominator in the law of large numbers we're trying to prove. Okay, so maybe I'll be a little bit so this value here is basically n times theta of lambda. Okay, and if I replace this curve by the curve e to the minus pt, which is, you know, roughly the same for p small, okay, and I look at the you know, if I let d lambda be the largest, well, let me call it dnp, is the largest real solution to the equation n minus t minus n e to the minus pt is 0, then this dnp is exactly n theta lambda. Okay, I mean, you can just you can see in this identity is the the identity that defined the Poisson, the Poisson critical survival probability. Okay, and then so I'll leave as an exercise. So if I define xt to be n minus t minus n 1 minus p to the t, and f of t to be n minus t minus n e to the minus pt, okay, then these two functions very closely track each other. So for any positive m, the difference between the two functions uniformly in p at most m over n and times between 0 and n is order 1. Okay, so so this so that's that discussion is sort of partly discussing this heuristic. It says that we can look at if we believe that the number of active vertices is oh, thanks, there's a missing minus sign there. If we believe that the active number of vertices is roughly going to track this, we may as well believe that it's roughly going to track this, because these two functions are basically the same, and this one is a little nicer because it exactly corresponds with the Poisson setting. Okay, so so this is a picture that we actually now want to understand in a bit more detail. If you like, what I'm plotting here on the one hand, so this sort of corresponds to the linear exploration. One vertex per time step is explored, and this corresponds to how we expect. This difference here corresponds to how we expect the number of active vertices to evolve. So at the start, when on average we explore more than one vertex per step, the size of that set should increase. And then as we deplete the finite stock of vertices in the graph, at some point that average number will dip below 1, and that difference will start to decrease on average and eventually hit 0 around this time n theta here. Okay, so what we'd like to do now is show that this random exploration process closely tracks the picture that's suggested here. So what we'll do in the next lecture, I hope I'll get through it in the next lecture, is sort of show that after some very small time g on the left, and until basically this time, which I chose the name d is the value I'm really going to focus on the right. The number of active vertices is very unlikely to dip below 0, and then a little bit after this time d on the right, the number of active vertices will hit 0. So that will suggest that we've explored a single component over this period of time. Okay, so obviously there's a little bit of work to do to put all that together, and the last it's I think up to here everything was rigorous rather than heuristic. Everything I said here is in the notes as well. So if including the heuristic discussion. So if you want to go over some of this in preparation for Monday's meeting, if there were points that were unclear, that might be good. But I'll stop the lecture there for now, and I'm happy to take more questions.